This is a talk I really wanted to give last Gardner 2 years ago, except it was going to be a little bit different because I was going to be the one who had proved that there were only 15. I spent months working very hard on this problem, and proof was not complete by Gardner, so I didn't give the talk. And as we've just heard, last year, Mikhail Rao scooped me and finished the proof. So I'm going to talk a little bit about how one could imagine proving this, what these proofs are like. Flash back to 2015, when the 15th tiling was announced. It was big news, as we have heard, the first one in 30 years. And if you look at this pentagon, this is the 15th pentagon that tiles. It's completely constrained. It's rather a remarkable pentagon. All of the angles are multiples of 15 degrees, and 4 of the 5 sides are in ratios of 1:1 or 1:2. The 5th one is fully constrained by the other sides and angles, so we can almost ignore that. So if you ask yourself, well, how many pentagons then can there be that are this nice? There's only a few thousand. Why had nobody searched this before? And I should say that's not the kind of search that Casey Mann et al. Did. It was a symbolic search. But immediately when I saw this, I said, well, okay, I have to write a search program to see what else there might be in this family or with smaller angular increments or whatever. And probably the reason this hadn't been done before is it's not totally trivial, just given a pentagon, to answer the question programmatically, does it tile the plane? But you can do it with a little bit of work. So suppose somebody gives you a pentagon. Here's what you do. You lay out one copy. You do this recursive backtracking search. So let's look at, say, the upper left edge there. There are a certain number of ways that copies of the pentagon can go against it. You have to try all of them. And for each of those, you have to look at another edge and try placing a pentagon there. You know what all the numbers are, so you can do this numerically. And at some point, you might reach a point like this where we see, oh, that angle is too small. There's not going to be any way to put a pentagon there. We can rule this out and backtrack. Now, this recursive backtracking search, it works with a little bit of effort. It's not going to give you a tiling. What it will do is if the pentagon that you have given it does not admit a tiling, then the program is not going to be able to place a large number of pentagons, and you'll know there's no tiling. If it is able to place a large number of pentagons consistently, then you can look at that particular one and say, oh, that's a type 3, that's a type 7, or that's a new one. So I ran this program over that class of pentagons I described, and it quickly found the type 15 and a bunch of others, no new ones. I changed the angle increment down to 1 degree and tried a bunch of other edge relationships and so forth. Didn't find anything new. So now what? Okay. I better hurry up, sorry. So the key is to do this search symbolically and not numerically. As we saw, the 15 types of pentagons are defined by relationships on their edges and angles and not by specific numbers. So if we go back to how this search works, let's imagine that we are doing a symbolic search instead of a numerical search. Here, we don't know anything about the pentagon. The sides and angles could be anything, but we still want to try. They're still labeled with A, B, C, D, E, and so forth. So suppose we're 3 pentagons into this search. Every new pentagon that we place induces new constraints. So for example, when we place the yellow one, we got the constraint that edge D is longer than edge B. And we place the blue one, we see edge C is longer than edge E. Angles A plus C plus D are strictly less than 360, and so forth. So it's a lot more work to do the search like this, but you can do it. Every time you place a pentagon and add the new induced constraints based on the placement, you have to verify the constraints are consistent. The length and constraints and the angle constraints are independent. You can use linear programming to solve those and make sure they're consistent. But the combination of the length and angle constraints yield geometric constraints that they have a geometrically realizable pentagon, and those are harder to do, but you can do that computationally as well. Once you go to all that work and you get your code debugged, which took me several months, you discover that the search space is enormous. And if you're not very careful with your search heuristics, you always go off on some infinite dead end in your search tree. So what I did was break it down into 29,000 cases based on inequality relationships among the, it's a very natural set of cases, and then you can have the program tackle each of them individually. Most of them yielded very quickly to this search. Some of them were hard nuts, and I had to go and look particular, why does this one fail? I need new search heuristics and so forth. That task was not done by Gardner 2 years ago. As Jaap mentioned, Rao had much greater insight than I did and was able to narrow the set of cases down to 371 by considering the different ways that pentagons could meet at a corner. And congratulations to Rao. I wish it had been me, but it's still wonderful to have this century-old problem finally closed out. Thank you.